So here's where we left off. So first of all, as of Wednesday, we were just talking, we hadn't gotten to the point where we were talking about the objects that we were using, but these are them, okay? There are these little blocks. And our quest is gonna be to determine to what degree things like the type of fabric or the type of surface, the surface area, and the weight of an object affect the amount of friction that's acting on it. And what we're going to do to determine the amount of friction is we're just going to lift up a ramp with one of these blocks on there. So you can see that like it's not moving. And so we know there's friction because if there weren't, it would be moving. So the higher I lift it, the more friction there must have been. And once it starts sliding, then we'll be like, okay, the angle at which it started to move is some indication of how much friction was acting on it. We don't know exactly what yet, but we'll be able to figure that out. And so our data is going to be, break it, you buy it. Our data is gonna just be initially what is the angle at which it started to slip, and we'll try it on the large wooden side and the small wooden side, and the large felt and the small felt. And we'll try it with stuff on there, metal bars. And just to be clear, when you put the metal bars on there, you have to tape them. But if you wrap tape around, then you're affecting the surface in contact with the track, so you can't do that. You have to kind of tape it to the sides or to the top. So it's a little tricky, but I have utter confidence that you all are going to be able to pull this off. And then, so your data collection, which I think most of you are going to be able to get done today, consists of angles. And what I want you to think about with the angles is a couple of things. One is, the precision and accuracy of your data matter. So ideally, you'll do things like, for example, take multiple trials. And as you're collecting data, compare the data you're getting with other groups under the same circumstances. So if they're measuring the large wooden side of the block you should all be using the same material. So if you're on the large wooden side, then go check with other groups. And if you're getting 72 degrees and they're getting 18 degrees, then something's wrong, something's not working. We did find, by the way, that at least one of these wooden blocks is sticky. It's got tape residue on it. And so it's like kind of gluing itself to the tracks. The tracks might be sticky too, they're not all the same. So we kind of want to like get rid of the ones that just don't, like if you have a track and it's like no matter what you do, you keep getting larger or smaller angles than everybody else, then your track is different. So don't use it, use a different one. And same with the block, like if we can't get these blocks to give us, like if your block and somebody else's block are different, so different that you're not going to get the same, even remotely the same results, then like figure out which one is more representative of the blocks as a whole and use that one. And that's not ideal, but it's realistic. So because this is real world stuff, like there is no right answer here. And so you're going to collect a bunch of data, you'll throw out your outliers, make sure that your data is good. I think I told you yesterday about the Physics Toolbox, did I tell you that? Physics Toolbox is an app. You can get it for both kinds of phones, and there is there's an option on there that says inclinometer. It'll tell you the angle, and you just have to be careful because most of your phones, like mine, have the camera bump. So if you lie your phone down flat on a surface that is perfectly horizontal, your phone isn't perfectly horizontal. It's at an angle. So you got to figure out how to compensate for that. What I do is I just set it on the track so that the camera bump isn't on the track like this. So now mine is correctly indicating the angle of the ramp, and you have to look at all of them. Like this one on my phone, the way I have it oriented, it's roll that I'm looking for, the particular axis. So this is about a 10-degree angle, and I can't see. This is about a 13-degree angle. So and I'm pretty confident in that because I've got nice flat surface on the back of my phone to work with. So you're getting good angles, you're getting good data, you're getting a lot of it, you're gonna collect data for all 4 sides of this wooden block, and you're gonna collect data with some mass on there, which means you may not today get to the point where you need what I'm about to show you, but this is really important. So the next piece, and you'll get here on Thursday for sure, possibly today. The next piece is to think about kind of a big problem, which is if you have a ramp like this with a block on it, then we've got a consistent free body diagram under the circumstances that we're describing. Now, there might be other forces, in theory, there could be other forces acting on this. There could be a big bird pecking at it from the side, and it might be, like somebody might have thrown it so that it's hitting the ramp really hard. But if you stick to our defined scenario, which is you just put the block on the ramp, no birds, nobody's throwing anything, and you just lift up the ramp, that means there's 3 forces on this. Those 3 forces are always the same 3 forces. The sizes and the directions might be a little different, but it's always the same 3 forces. Here's what they look like. If you're in regular physics, you're gonna draw free body diagrams the way that I think is most meaningful, which is you use a rectangle to indicate the object. I use a rectangle because as soon as I draw a rectangle like this, I know, oh, that rectangle is resting on a slanted surface. That's super handy to know. If you're in AP physics, you can't do that. They don't want to see rectangles, they want a dot. This is our object, okay? But the forces are the same. And one of the forces, the easiest one to think about, is the gravitational force. That is pulling straight down on the block. When we draw free body diagrams that show forces acting on things, we draw forces as arrows pointing away from the object. This is the gravitational force. The gravitational force, we could write F with a little g, which stands for the force of gravity. That is also equal to the object's mass times the constant g. This g does not stand for gravity. This g stands for the acceleration of an object in free fall close to the Earth's surface. That's what it stands for. And it has a value of 9.8 meters per second squared. It's a constant that tells us an acceleration. We also call that force weight. The weight of this object is its mass times the constant g, which is the acceleration of an object in free fall close to the surface of the Earth. That is also the force of gravity. That's one of our forces. In AP Physics, you'll draw that force the same way and label it, pick one of those, right? Just pick one, mg. And then our other force, well, there's 2 more forces. One of our other forces is the force of friction. So if we have an object like this that isn't moving, so it is moving, let's stop that, it's not moving. How do we know what direction the force of friction is? Friction opposes motion. It's not moving. So how do we know what direction the friction force is? We ask ourselves a question, which is, if we turned friction off, would it move? And if so, in what direction? If we turn friction off, like we can emulate with the cart, then it would move down the ramp, which means the force of friction is opposing that tendency of motion. It's not moving, but the reason it's not moving is because the force of friction is opposing the direction in which it would move. So our free body diagram in AP Physics land would include that arrow as well. Then the last force is what? There's one more force. It's resting on a surface. Yeah. The normal force. And I've had 2 people now call it the natural force. Remember I made a bet with you? You already lost. So it's the normal force. Normal means perpendicular. Perpendicular to a surface. If an object is resting on a surface, supported or partially supported by that surface, there's a force from that surface. That force is perpendicular to the surface, which means our normal force is in this direction. In AP Physics, you draw it in the same direction, like this. And you can see why I prefer my rectangle, because When I draw my rectangle, then I can see the friction force is parallel to the surface, the normal force is perpendicular to the surface. In AP Physics land, it's like, well, I don't know where the surface is. I can infer it by looking at the forces, but I can't infer it by looking at my object. I like this better. Having said that, if you want to use a dot, you knock yourself out. It's not wrong, okay? So here's the problem with this. We have not talked yet about how to deal with forces mathematically as vectors, but we did talk about how to deal with vectors in general when we were talking about displacement, velocity, and acceleration, all of which are vector quantities. And we talked about the idea that there's this like 90-degree thing. So here's something to think about with forces. If we're trying to figure out how forces combine, it's pretty easy to think about it if they're in opposite directions. If I have one force to the right and one force, wait, that's to the left, one force to the left and one force to the right, and they're the same, then they balance each other out. If one is bigger, then the overall force is in the direction of the bigger one, right? And it's like the difference of the two forces. It's intuitive. But what do you do when they're not at right like aligned with each other? These two forces are at right angles, and this one isn't at any like easily identifiable angle to the other two. How can we tell if it's balancing out or not? And the answer is we're going to break forces into components, just like we did with kinematics. How do we know which forces to break into components? We can break any of these into components. Components are just two forces that add together to make a third, or 11 forces that add together to make a 12th. Like it's just pieces that can be added together to make something else. Those are the components of something. We don't want to just like randomly pick them. What we want to do is pick something that's right. We have a lot of options for that, and something that makes the work as easy as possible. And it turns out that in general, the way to determine how to break forces into components is to ask yourself how you can arrange your axes so that you have the minimum amount of vector breaking up to do. So if we think about our standard frame of reference, where we have an x-axis and a y-axis, up is generally positive, to the right is generally positive. Then we have one force that's not aligned with that, that's the force of friction. Two forces that's not aligned with that, the normal force. And if we think about the motion of the block, now it's not moving now, but when it starts moving, it's going to be moving in this direction. We also have motion, which means acceleration and velocity, that is not aligned with this axis. Could we solve the problem? Yeah. But you know what would make it easier is this. If we rotate our axes so that they match up with the parallel and perpendicular dimensions relative to the surface. Because we've got two forces that are parallel and perpendicular, and the motion of the block, if it starts moving, is going to be parallel. That means we only have one force that we need to break into components. And here's where it gets, for some of you, you're going to be like, oh yeah, okay, got it. For others of you, this is just the first round of many, many, many rounds of practice. Here's how we're going to do that. One of these forces, it's not forces, but components, one of the components of this gravitational force is going to be perpendicular to our surface. So that's going to be a force in this direction. The other component of our gravitational force is going to be parallel to our surface. That's going to be in this direction. These two components add together to make the real force of gravity in the straight downward direction. We're going to use trig to do this. You don't have to know trig or remember it, but if you do, this will make a little bit more sense to you. In order to figure out the trig, we need an angle, and it turns out that the angle of the ramp with respect to the horizontal is going to be equal to this angle right here. I'm not going to demonstrate that proof to you, but if you're interested, I can show you in 5 minutes. Super easy proof that just involves some geometry and some like basic triangle stuff. That means that the magnitude of this component right here is going to be the weight of the object, the force of gravity acting on the object, which is equal to m times g, times the cosine of the angle of the ramp. The magnitude of this component is going to be mg times the sine of the angle of the ramp. The direction of this force depends on the axes that we've come up with. The way I did this right here, this is in the negative direction, and this is in the positive direction. But you know, if you have your positives kind of tending to be up and to the right, then if your ramp had been sloped the other way, like I drew my ramp the other direction during first period, and I ended up with the parallel component of the gravitational force being in my negative direction. The positive or negative just tells you if it's in the positive or negative direction, which you determine when you draw your axis, right? So this is valid, and this is equally valid. I've got my coordinate axes here, so it's really clear what my directions are going to be. That is going to take some of you some practice. Others of you are like, got it. Even if you've got it and you completely understand it, what you might find is if you're like me, that it's going to take you a while just to get the drawings right. And I know that sounds weird because it's like, well, how hard is that? And for some of you, it's going to be really easy. But what I found when I was first drawing these is that I would like draw my object like this, and then I would have like the gravitational force. That's, okay, I actually drew a straight line. But I would draw it more like this. I'd draw my gravitational force like this, and then I'd break that into components that were like this, and this isn't at all what we're trying to do. This doesn't match at all with what I just drew. It's superficially similar, but this is nowhere near an accurate enough drawing. So I've had, in the past, I've actually had students where because the spatial part is so difficult, we've had to make a square, and they have to like tilt it and use the square as like a double-sided square ruler to get all their forces and arrows and parallels and perpendiculars aligned. So if you have trouble drawing these things, I can help you with that. So this ultimately is going to be our free body diagram for this whole activity. The whole thing, this is the only free body diagram we have. Now what you'll notice is that the normal force, if nothing else, is constantly changing direction as you lift or lower the ramp. The normal force is always perpendicular to the ramp. So when the ramp is perfectly flat, the normal force is perfectly vertical. The steeper the angle of the normal force. So we know that directions are changing, and the components of the gravitational force are going to change with the angle. So it's not always the same magnitudes, but the same basic diagram will cover 100% of the scenarios that we're looking at here. 3 forces, 1 perpendicular, 1 parallel, 1 straight down, that we break into 1 piece that's perpendicular and 1 piece that's parallel. We're effectively going to think of this as 4 forces. The normal force, force of friction, the perpendicular part of the gravitational force, and the parallel part of the gravitational force. And that free body diagram is going to allow us to start doing some calculations. Most of you won't get there today though. You'll get there on Thursday for sure, but I want to make sure that you have this to start with. Your big goal today is to try to collect as much data as possible, really good data. If everything goes smoothly, you should be able to say, hey, when I had it on the large wooden side, we lifted it 10 times. It ranged from 18 degrees to 23 degrees, and on average it was, whatever, 19.4, and checked with other groups, and they had roughly the same range and roughly the same set of averages, okay? So if you, that's the degree to which we want to be confident about our numbers, and we have to work together to do this because you may have the oddball block or the oddball ramp that is sticky or less sticky than the rest of them, and your numbers are just wacky. So if that's the case, we gotta find you a different system to work with. More bad news. We don't have too many of these, which means that those of you who prefer to work in really small groups are gonna be sort of auto lock. You're gonna have to find a larger group to work with. Just dive in, like most of the students in this class with probably only 10 to 15 suggestions, exceptions are nice people. The 10 to 15 people who aren't nice, I don't know, like you're gonna make their lives miserable too, so it's a win-win. And so what I'm hoping is that by the end of the period, we can amass at least most of the data that we need so that on Thursday, we can start calculating actual magnitudes of forces of friction. All right, any questions before you get rolling? Okay, let's make it happen.
Yeah, all of us.